Okay, hello everybody. I'd like to get started. Can someone please confirm that you can hear me?
We can.
Yes, we can.
Okay, thanks. Okay, so repeat an announcement that I made last time, which is that there's going to be a quiz tonight. All of the logistical details are on Canvas. Also on Canvas, you can find information about what will be covered on the quiz. I will have 2 question and answer sessions today, so I won't be bringing any prepared material with me. I'm just there to answer your questions. And the times for these sessions are as shown, and the Zoom links are on Canvas. Also, remind you, if your Penn State user ID starts in the 2 letters PD through SD, you should make sure you ask a question today so that everyone can get extra credit. What we're going to cover today is reflection and refraction. Then we'll talk about what happens when 2 objects have the same index of refraction, which I'll explain what index refraction is as well. We'll talk about how rainbows work, and finally, how we make images with lenses. We'll probably just get started on that last topic. So last time we were talking about plane mirrors, and I want to do an example using 2 right angle mirrors here. And the example involves figuring out how many images are formed by 2 perpendicular mirrors using that the angle of incidence is equal to the angle of reflection for light rays that are bouncing off of a plane mirror. And for our purposes, we have an object, a red ball. Light is reflecting off of that ball from some source. And the question is, when the light reflects off that ball, are there ways that it can bounce off of these mirrors so that the light comes into your eye, which is shown over there on the right? And so let me just draw one example of such a ray. So we can have the light coming down like this, and then it will bounce off. And if I drew things correctly, which I sort of did, then this angle of incidence is equal to this angle of reflection. So the question is, how many other cases are there like this? And first, though, I have to point out that what the person who is looking here will see is the light comes into this person's eye in that direction. And so what your eye does, and what a camera does when the image comes on film, is it basically extrapolates back to the point where it looks like that ray came from. And you can't really do this with just one ray, but if you have multiple rays, then your eye can figure out your eyes can figure out what the depth is. And in any case, what your eye effectively does is it extrapolates this ray here back, so that there's an image behind the mirror, effectively, as shown. And we can do the same thing for 2 different possible configurations. So here's the one I just drew. I should say 3 different configurations, but it's also possible to draw 2 more configurations. The first one is relatively easy. That's this black one up here. So here's where the angle of incidence is equal to the angle of reflection. And what the eye then does is extrapolates the image as though it were coming from back here. And then the more complicated one is shown in magenta, because that has to undergo 2 bounces off the mirror. So there's one here where the angles are identical, and one here where the angles are also identical. And that particular image will look like it's back here. So these are 3 possible, 3 images that you would see if you had an object over here and you were looking from that position there. Notice that you could be looking from probably, you know, a position over here as well, and also see 3 images. Those images would not be in exactly the same place, but you would also see those images because you could probably draw 3 different light rays that would go into your eye from this position. Okay. So let me now move to the subject of refraction. Refraction is what happens when light moves from one medium to another. So we've talked about reflection, where it stays in the same medium. In this previous figure, the light was always in air. It was bouncing off of this mirror, but it was always in air. Now we're going to consider the case where the light can move from, say, air or some material with index of refraction N1 and water, for example, with an index of refraction N2, and N1 and N2 are not the same. The meaning of these indices of refraction, these N's, are as follows. So light, when it moves in vacuum, or for that matter, when it moves in air, moves at the speed of light, c, which is 3 times 10 to the 8 meters per second. And we're going to talk about that a lot when we get to relativity in about a week. The index of refraction of the vacuum is defined to be 1. The index of refraction of air is very, very close to 1. It's like 1.001 or something like that. But there are other materials that have much higher indices of refraction, like 1.5 for glass and 1.3 for water. And when light encounters a material that has an index of refraction that's higher than 1, is its velocity gets reduced by that factor. So the velocity equals c divided by n for a medium that has an index of refraction n. So obviously in vacuum, where n is equal to 1, then the speed of light is c. But in water, for example, the speed of light is c divided by roughly 1.33. So it's 3/4 of the speed with which it moves in vacuum. Now the frequency of a light wave as it's moving from one medium to another, from air to water, say, can't change. But if the velocity is changing by the expression for waves, that the velocity is equal to the frequency times the wavelength, if the velocity changes, if it gets divided by this n factor, then with the frequency being constant, the wavelength is going to have to change. And in fact, what happens is that the wavelength goes to lambda over n. So for light, effectively we have c equals f lambda, which then becomes c over n equals f lambda over n for in some medium. The main takeaway here is that the wavelength basically shrinks when light, in addition to light slowing down, its wavelength also shrinks. So you can go through the trigonometry using that fact, and that's shown over here. I'm not going to go through this in any detail, but let me just highlight the important elements of this figure. So I already indicated that there are 2 different indices of refraction here, N1 and N2. There's an angle of incidence, which you remember is defined with respect to the normal. And in this case, the normal is a perpendicular line to the plane of the interface between these 2 materials having index of refraction N1 and N2 respectively. So that's the angle of incidence. And then over here, we draw another equivalent normal. This is the angle of refraction. So with reflection, we had an angle of incidence and an angle of reflection, theta sub I and theta sub R. Now we have an angle of incidence, which could be labeled theta sub I, and an angle of refraction, which unfortunately uses the same letter R, theta sub R. Typically, though, we will refer to these angles by the subscripts 1 and 2 corresponding to the indices of refraction 1 and 2. So using some relatively straightforward trigonometry, if you look at this diagram, and this is done in the text, I won't do it here, you can basically write down this expression down there, which you can simplify to what's called Snell's law, which is shown here, which says that the index of refraction of medium 1 times the sine of the incident angle theta 1 is equal to the index of refraction of medium 2 times the angle of refraction times the sine of the angle of refraction theta 2. So if n1 is less than n2, which in this diagram is sort of implied because we might have, it looks like we have air up here and water down here. If that's the case, then what will happen is the light rays coming in will have a larger angle with respect to the normal when they enter, when they're in the air, I should say, than when they're in the water. So as they go from a lower to a higher index of refraction, they will hug closer to the normal. Okay, so here's a picture that maybe illustrates that a little clearer. So here's the incident angle theta 1, and here's the refracted angle theta 2. And you can see that theta 1 is larger than theta 2, which is what I was trying to say before. The refracted ray moves closer to the normal than its angle in the medium n1, provided that n1 is less than n2. Okay, so let me do an example now using refraction to actually show that you can generate an image through purely refractive effects. So what's shown here in this diagram is a coin down at the bottom of a pool. That's circled down there at the bottom. And we choose a single point on the coin and say, okay, some light reflected from wherever, from the sun above, from that point in the coin, and it goes up, and those rays have these particular angles as shown, okay, like that and like that. And then they emerge at the water-air boundary, which is shown there. And when they hit that boundary, they are going to refract. So if I draw the normal here, what you see is that there's an incident angle here and a refracted angle here. And because it's going from water with a higher index of refraction to air with a smaller index of refraction, the light bends farther away from the normal than it had in the water. And the net result from this, if you consider not just these two rays that I've drawn here, but lots and lots of rays, is that they will all look like they are coming from a coin that is right there. So that's not where the coin actually is. The coin is actually out the bottom of the water here. But because the light bends due to refraction in this particular predetermined and deterministic way, as the light goes from the water to the air, it will appear as though the coin is actually in the location drawn, a depth d sub a, where a stands for apparent, rather than this depth d. So the question is, what is that d sub a? And I hasten to add that all the angles in that figure have been exaggerated just to make it easier to figure out, to see the trigonometry and the geometry of the situation. So what we want to do is show that d sub a is equal to d divided by n. So the perceived depth, the apparent depth, is given by the true depth divided by the index of refraction of the water in this case. So let's do that. So the steps are going to be first to draw in so a bunch of normal vectors, which I've done with these red dashed lines, and then draw in what the various refraction angles and incident angles are. Then we're going to find expressions for the tangents of those angles and write down Snell's law, and then use a small angle approximation in order to simplify things and then solve for d sub a. Now notice the way I've drawn this figure, the small angle approximation doesn't look like it could be used. But recall that I have exaggerated all these angles in order to make it easier to see what's going on. So the angles are in fact small enough to use the small angle approximation. So let me just go through what those angles are. So the angle of incidence, and we'll just look at the ray on the right hand side. It's behaving exactly the same as the ray on the left hand side. But the angle of incidence is shown by that theta sub I there. And then the angle of refraction is shown here. And you can also see that this angle in here is the angle of refraction. So what we can do is write down that the tangent of theta sub r, the angle of refraction, is just the opposite over the adjacent, which in this case is x divided by d sub a. And we can write that the tangent of theta sub I, maybe it's easier to look at this theta sub I in order to calculate that, is this distance, which is also x, divided by this distance, which is d. So that's x over d. And previously we saw that the tangent of theta sub r was x over d sub a. And we can just write down Snell's law, which is n sine theta r, so it should be like n1 sine theta r and n2 sine theta I, but n1 is just equal to what? Anyone tell me? Yeah, it's just equal to 1 because it's in the air. So what I do is I simplify Snell's equation by just writing it like this. So there's effectively, a 1 in front here that I'm not actually writing out. Okay. And we can simplify all those things using the small angle approximation, and that's done here by just removing the tan and sine as appropriate. And then you can solve for d sub a, and you can show that it equals d divided by n in the small angle approximation. So the conclusion that we can draw from this is that refraction can produce images. So the image in this case is this little coin, which appears to be right here. So there's a little image of the coin that is higher up in the water than its actual position in the water. And that was due to purely refractive effects. Okay, so I'd like you to take a look at this concept question here. I'll set up a poll while you're looking at it. So what will you see if a solid with index of refraction n is immersed in a liquid with the same index n? So we're going to explore more about refraction and refractive indices now. Okay, get your answers in, please. All right. So people are pretty much evenly split between answers A and B. So let me show you this video. So take a second here. Wrong screen. Okay. So everybody watching? So we're pouring in a liquid that has the same index of refraction as the glass tube. And I hope you can see, or not see, that the tube has effectively disappeared because the index of refraction of the liquid is the same as the glass that was inserted into the liquid. And just to keep things consistent, the fluid inside of that little test tube is the same fluid as is inside the beaker. But that doesn't particularly matter if instead of that little test tube, you put in some solid glass that had the exact same index of refraction as this material, as this liquid has, then the same thing would happen. You would not see that glass inside of the liquid. Without the index of refraction, with the index of refraction being the same, there's no light bending. And if there's no light bending, you won't be able to make an image with your eye. Okay. So I'd like to ask another question about refraction. And this question has to do with what happens if instead of the light originating from above, as we've shown here, at some angle of incidence theta I, and then going off at some angle of incidence theta 2, where we've assumed that N2 is greater than N1. So the theta 1 is going to be larger than theta 2 in that case. What happens if the light instead is coming from below? So as we increase this angle here, theta 2, so now the light is coming from below. We increase this angle to larger and larger values. What happens? So I'll start a poll so we can answer this, and I'll show you what the question is, what the possible answers are. Okay, get your answers in, please. So most people chose the answer B, which is the correct answer. And you can see that by looking at the Snell's equation and just rearranging terms slightly, which I've done here, and then asking what happens if N2 is greater than N1, so that this prefactor here is larger than 1. As we increase the angle theta 2, sine theta 2 gets larger and larger. And eventually, what mathematically bad thing could happen? You can answer in the chat. So again, N2 divided by N1 is larger than 1. And we're increasing this angle theta 2. That's right. The product of N2 over N1, which is larger than 1, times sine theta 2 could eventually become larger than 1. And then we're going to have something like sine theta 2 equals, I don't know, 1.23 or whatever. And that clearly cannot work. That is mathematically impossible. So when we get to a large enough theta 2, we run into the case that that Snell's law sort of breaks down, or maybe a better way of putting it is Snell's law is telling us something else must be happening. We define something called the critical angle, theta 2, as the angle that gives theta 1 equals 90 degrees when n2 is larger than n1. And then anything above that, you would get this mathematical problem. So this is the critical angle. And the way we calculate that is simply by saying, okay, sine theta 1 is equal to sine 90 is equal to 1. And then I can just rewrite this expression like this. And finally, can just solve for the angle theta 2. So for any angle theta 2 that's larger than theta c, what will the light do? So if we're looking over here at this diagram down at the bottom, so what I'm asking is, okay, I increase theta 2 over to this value, and I get some light refracted out. What happens if I go, over to here, above theta c? So this angle theta is larger than theta c. What happens to the light? So some people have written down that it reflects, that you get total internal reflection, and that's correct. The light will just bounce down this way, and none of it will be refracted. None of it will leave the interface. It will stay in the glass or in the water, whatever N2 represents. So here's a picture of what's going on. So purely vertical light remains vertical and doesn't get refracted at all, or reflected. Maybe a little bit gets reflected, but it's not shown here. And then if you have a slightly larger angle, theta 2, then you will get a bunch of light that gets refracted and some that gets reflected. And as you gradually increase, that angle, as you gradually increase the angle theta 2, then eventually you reach this angle, the critical angle, and at that point, you'll only get light that's traveling along the interface or that gets reflected. And finally, if you go to even larger angles than the critical angle, so now the angle in here, this angle is larger than the critical angle. Now all the light is reflected and none of it is refracted. So this is known as total internal reflection. And I'm sure that some of you know what practical applications there are for this. Can anyone mention it in the chat? Yeah, fiber optics. So fiber optic cables consist not of just one type of glass or plastic, but actually some sort of glass or plastic with a cladding around the outside, sometimes multiple claddings, which are designed to have different indices of refractions to enhance total internal reflection. Because you want as much of the light that you send in at one end of an optical fiber to emerge at the other end. And the one way to ensure that you get most of that light is to have all of it in total internal reflect and none of it, escape the fiber optic cable itself. Good. Okay, I want to add a new concept called dispersion here, and we're only going to talk about this qualitatively. And it's really a simple extension of our discussion of the index of refraction. And basically, we just take the index refraction and observe that it actually depends on the wavelength of the light. So if the index refraction depends on the wavelength, then that means that different wavelengths of light that enter a medium will be refracted differently. So Snell's law that you write down for each different color of light, for each different wavelength of light, depends on the index refraction that light experiences. And if that index refraction depends on the wavelength, then the refraction angles are going to depend on the wavelength. And so you can make a device, in particular this prism here, where light that has multiple colors goes in one side, and then the different wavelengths get bent at different angles because the index refraction depends on the wavelength. So they experience different refractions as they go through the glass, and they emerge on the other side as their different constituent colors. So white light goes in, and you can sort of see it reflected here in the prism. And then on the other side, what comes out is the white light basically divided into its constituent colors and wavelengths by the prism. So we can use this to explain how rainbows work. And I know that there are some people who think that if you understand how things like rainbows work, it takes away some of their magic. I actually think it's just the opposite, that understanding how they work enhances the beauty of a rainbow. So let's discuss how a rainbow might be formed by using these ideas of dispersion, reflection, and also refraction. So we're going to assume is that all of the rain in the sky consists of perfectly spherical rain droplets. It's a reasonable approximation. It's not perfect, obviously. And the physical situation is that the sun is behind you, and in front of you is rain with all these spherical droplets. So the sun's rays are hitting those droplets, and then some of them are bouncing back, and you can see the light that comes back from them. So what happens to that light? So the thing that happens is shown in this little figure here. So the sunlight goes into the drop, and when it goes into the drop, it experiences refraction, and I've drawn like the normal to the surface of the raindrop sphere here to indicate where the angles are going to be measured. And what you can see is that the red, for example, has a larger angle than the blue light that's in the sunlight, because the sunlight consists of all different colors. And so it's going to undergo a different angle of refraction when it enters this raindrop. And then over here on the back side of the raindrop, some fraction of the light will reflect off of that boundary. Most of it is going to keep on going. It's going to refract again and basically just leave, and you won't see that. But some fraction of the light reflects. And then when it hits this boundary here, emerging from the raindrop to the air, it undergoes another refraction, which further spreads out the different constituent colors in the sunlight. So now what do we see if the light coming from the raindrops looks like that? So if you're standing down here, and you're looking up at this rainbow, let's imagine you're a little bit smaller and closer. What you will see is this blue light coming from the raindrop that's down low in the sky. For a raindrop that's up high in the sky, you might see the red. So what this means is that based on this argument, we would expect for light that goes through a raindrop and undergoes one reflection at the back and two refractions, one at the entrance and one at the exit, will produce a rainbow that will have red light up high and blue light down below and all the other colors in between. Even though you might think just the opposite, looking at the way the colors are coming out, because here blue is on top and red is on bottom. But what actually happens though, if our model is correct, is that the red light will go into the ground from the droplets that are low in the sky, whereas for the droplets that are high in the sky, you'll see just the red light because the blue light will go over here somewhere, and vice versa for the blue light and the low down droplets versus the higher up ones. Okay, so let's draw a better picture of this shown here. So here's what we actually see. If you look at a rainbow, the colors vary from red up on top to blue or violet down below. And the angle at which that rainbow occurs is 42 degrees, which you can calculate by going through the complicated geometry of this refraction, reflection, and second refraction when it exits the raindrop. And what you will see is the red from the higher raindrops and the blue from the lower ones. And that's why the ordering looks like that. Okay. So there's what a rainbow looks like. And we have the red, higher up and the blue lower down. So I hope you can see that. The other thing that's sometimes visible, if you're lucky, is a secondary rainbow. And that's kind of shown here in between these lines. It's kind of faint. Maybe you can see it. And one thing you can notice is, first of all, it's at a different angle relative to where you might be standing, sort of over here somewhere. So you see something at this angle and you see this one at a different angle. And the other thing you might notice is that the ordering of the colorings in the rainbow is reversed. So red is on bottom and blue is on top. So can we explain that? And the way to understand it is to think, is there another way that light can bounce around inside of a raindrop and we can still see it? And the answer is yes. So the light can go through hitting basically a lower point on the raindrop and then undergo two reflections inside. So it refracts and then it reflects and then it reflects again and then it refracts coming out. Each time it reflects here and here, light also leaves the raindrop. And because of that, the intensity of the secondary rainbow is going to be lower than the intensity of the primary rainbow, because more light is going to be lost if you have two reflections than just one inside the raindrop. But anyway, what you see is that the red light from the upper raindrops is going to come out above where you can see it. So you'll see the blue light from the upper raindrops and vice versa for the lower raindrops. And consequently, the ordering of the rainbow, the secondary rainbow, is just the reverse of the ordering of the primary rainbow for this reason. Now, the rainbows that we normally see are basically half arcs, or maybe even less of an arc, because we're not really up high enough. If you stood on a cliff and looked down at a rainbow, first of all, that might be a little dangerous because you're up at a high place and there's rain falling, so maybe there's a thunderstorm, so I don't recommend doing this. If instead you're in an airplane, then you can see more of the rainbow. In fact, this person was lucky enough to see the full circle. So you can see the full circle of the primary rainbow. Here's a little bit of it circled there. And you can also see the secondary rainbow, which doesn't quite make it into the photo, but goes up like that and around. Okay, enough about rainbows. What I'd like to do next is talk about applications of refraction and reflection, focusing on refraction and using thin lenses to employ refraction in order to make images. The adjective thin here refers to the thickness of the lens relative to something called the focal length, which will be defined in detail later. But let me just draw a quick picture so we know what the terminology is. So if this is a lens made out of glass sitting in air, and you send some light into it, that light will go to a point that is some distance f away. That's called the focal length. And the definition of a thin lens is that the thickness of this lens that I've drawn here might be less than 0.5 millimeter, whereas this focal length could be 10 centimeters. So that's the definition of thin, is that the lens is really thin compared to that focal length. And this is a reasonably accurate assumption, and it helps simplify things. We're also going to assume actually that lenses have essentially zero thickness, because that's even easier. And furthermore, that lenses are symmetrical about their central plane. So here's an example. There's a lens that's symmetrical about its central plane. You could, of course, have a lens that looks more like this. So it has different curvatures on one side or the other of the central plane. But we're going to focus primarily on the ones that have symmetry about the central plane. Okay, so the approach we're going to take is first the geometrical approach, which means we're going to sort of sketch things to figure out where the image might be for an object given a particular lens and a particular lens's characteristics. And then we're going to get quantitative and work with something called the lens equation. And I think this is a really useful progression to follow, because the geometrical approach gives you a physical intuition to where things where images will end up. And then when we get quantitative, we can use the geometrical approach to check that our quantitative answer actually makes sense. So there are two different kinds of lenses. They're called converging and diverging. They're also known as convex and concave, and I'll use these terms interchangeably. In the figures over here to the right are shown the two basic properties of these kinds of lenses. So the convex lens at the top, if you have parallel rays coming in, and these parallel rays, by definition, if they're strictly parallel, would have to have come from an object that was infinitely far away. So it's an approximation that we get parallel rays from some object like this, but it's a good approximation for objects that are sufficiently far away. Then that parallel ray comes in and gets refracted. It goes down and meets all the other rays that come in parallel at this point, which is the focal point. And I've only highlighted 2 of the 5 rays that are drawn here, but they all focus there. By contrast, the concave lens shown down below, the light that comes in gets refracted in such a way that it points out, like that shown. And then what happens is these rays that have been refracted all look like they're coming from this focal point over here on the left of the lens. So that's how a concave lens works. And let me just draw quickly what's actually going on inside this convex lens. So if that's the lens, let me draw a little bigger, make it easier to show what's going on. So we have light that's coming in like this, parallel. And then this lens is made out of glass. So if we draw the normal to the glass-air interface and ask what happens to that ray that's coming in, well, it's going to move closer to the normal. So it's going to do this when it enters the glass. And now it's going to exit the glass. And when it exits the glass, we draw the normal there. It's going to go exit the glass farther away from the normal. And so it's going to be pointing sort of down like that. And eventually what will happen is what's shown in this figure, they'll all meet at this point over here. But this is what's happening in detail. We're getting essentially two refractions that happen as the ray enters the glass and as it exits the glass of the lens. And the net result is that all the rays that come in parallel converge at the focal point. That's for a convex lens. I encourage you to draw a similar figure that I drew for the convex lens for a concave lens. And you'll see that what happens is all these rays get bent out and they look like they're coming from the focal point behind the lens. Okay, so the lenses that are shown here are shown with a finite thickness, but we're going to be assuming that the refraction actually takes place right in the central plane. And if you look carefully, like right here, that's indeed what is being approximated here. So here's the central plane, and right along there is where the bending is assumed to take place. Okay, it's an approximation, but it's a pretty good one. And that's what we're going to assume. And we're also going to measure all distances from the central plane. That central plane that I just drew and erased is this line that goes right through the middle of the lens. And likewise, over here, this line that goes right through the middle. So that's where we're going to measure all distances from whenever we have occasion to measure distances. All right, so there are three sets of rays that are very useful to keep in mind to figure out what kind of image is going to be produced for a given object. So let's start out with converging or convex lenses. So the first set of rays are parallel rays. And we just talked about those a second ago. So parallel rays that come in will all converge on the far focal point. Another set of rays you can have are rays that are emerging from the focal point on the left-hand side of the lens in this case. What will they do when they go through the lens? What will they look like on the other side, on the right-hand side of the lens? And in that case, as you could imagine from symmetry arguments, they will come out all parallel. And finally, if the rays go right through the center of the lens, then they will not be refracted at all. So those rays are not bent at all. They just go straight through. So those are the three sets of rays. There's parallel rays coming in. There are rays coming from a focal point going out, and they emerge parallel. And then there are rays that go through the center. For the case of diverging or concave lenses, it's a little bit trickier. So here, if we have, just as above, parallel rays coming in, what they will do is, as we drew earlier, they will emerge and look as though they are coming from this near focal point. Now the focal point is on the same side of the lens as the rays themselves, whereas for the converging lens, the focal point here is on the opposite side of the lens as all the light coming in. Okay. The second set of rays for a diverging lens are rays that are coming in that are all directed before hitting the lens towards the far focal point. So these are all pointing towards the far focal point. And if that's the case, then when they hit the lens, they will emerge parallel. And finally, just as with the converging lens, the diverging lens, if you send rays, excuse me, through the very center, they will emerge undiverted. They will not be bent. Okay, looks like I've run out of time, so I will stop there. I remind everybody there are some extra office hours today, 2:30 to 3:30 and 5 to 6, and the Zoom links are on Canvas. Those are just Q&A sessions, so I won't have anything prepared. I'll just be there to answer your questions in preparation for the quiz tonight. I'll stick around for a few more minutes if anyone wants to ask questions. So bye-bye.
With the example of the prism, you were saying that the lights essentially experience a different n value as
Right.
they're. So I was wondering, like, n is a material property, though, right? So like, how does that work exactly? I'm just a little confused as to what you mean.
It's a material property, but it could still depend on the wavelength of light that's going through the material. So the index of refraction determines how fast the light moves in the material. And what this basically says is that red light moves at a different speed than blue light in glass, for example.
Okay. So it's more like a scaling factor, right? On the various speeds of the different wavelengths, mayes.
Did you say it's a different scaling factor? Is that what you said?
Yeah, kind of. Is that like a reasonable way to think about it?
It's another way of looking at the index refraction. You can either think of it as affecting the speed or the wavelength. They're equivalent. But I guess it's not obvious. I can't think of an obvious example of a material in which the speed depends on some quality of the thing moving. I mean, light is kind of weird that way.
Mm-hmm.
But this is an intrinsic property of materials nevertheless, because basically what you will find is that the dependence of the index of refraction on wavelength has some dependence for glass, and then for water it has some other dependence.
Gotcha.
So in that sense, it is an intrinsic property of the materials, but it varies with wavelength in a specified way for a particular material.
Makes sense. Thank you.
Yep. Okay, So I can answer this question. It's question 2 on the exam. Hold on a minute. So I don't know if you can see this here. So are you able to see that, what I have drawn up there? Okay. So the basic idea is that you have these two expressions over here. The first one describing interference, and the second one diffraction. And the basic idea from this question is that, as worded, it tells you that you have a double slit experiment and the spacing between the slits is exactly 5.3 times larger than the width of each slit. How many constructive interference fringes are observed within the central diffraction maximum? So that last phrase, within the central diffraction maximum, says, I want to find out how many fringes are in between the 2 points that are highlighted just now with my pen, between the dark fringes that are around the central maximum due to the diffraction pattern. So the diffraction causes there to be this overall envelope on the interference pattern, and the diffraction pattern experiences its first dark fringe at these arrows here symmetrically around the central axis. And that can be found when, by setting in this expression, A sine theta p equals p lambda, by setting p equals to 1. Okay, so we know that theta p in the small angle approximation will be equal to lambda over A. Okay, and then the question is, how many of the interference fringes can we fit inside there? And in order to determine that, you need to count up how many interference fringes are within an angle theta p, because it's within basically this angle here that we're looking, because that's the angle that has the first, that points to the first diffraction minimum. We want to know how many interference fringes are inside that region. So in order to figure that out, we need to basically just set the 2 angles the same. In other words, the angle that you use to find the first diffraction minimum is the same angle that you will use to figure out how many interference maxima there are. Because what you'll do is you'll just say, okay, these 2 angles, theta m and theta p, are the same. Meaning that at that angle theta p, which is where the first diffraction minimum is, I want to know, what order of the interference pattern reaches out that far an angle. And the way to figure that out is by setting these 2 equal to one another and then solving for m. So if you do that, basically we have that theta 1 is equal to lambda over A. That's what I just wrote before, or theta p is equal to lambda over A. And so we put that theta 1 into this expression here, and we got this expression from d sine theta equals m lambda, and we just simplified that to d theta equals m lambda. This is for interference. And then I just plugged in this theta in here. And so that tells me that d lambda over a is equal to m lambda. And you can see that the lambdas cancel out. And you end up with this relationship. So what this tells you is that the number of orders of the interference pattern, where m is the order, that fit within the first diffraction minimum is given by d divided by a, where d is the distance between the interference slits and a is the width of each of those slits. Now we know that that's given in the problem as 5.3. So somehow we have to relate m to 5.3. And basically this says that the fifth m equals 5 will fit underneath the first diffraction minimum, or underneath, I'm sorry, the central diffraction peak. So if you look at this figure over here, this peak, or this one maybe right here, should be the m equals 5 peak. That's the very last one that fits inside of the central diffraction envelope. Now, the way I've drawn it, it looks like it's actually 1 to the third peak because I didn't put enough wiggles in there. But that's the general idea, is that the m equals 5 interference bright fringe will appear just before the first diffraction minimum, because the first diffraction minimum happens when m is 5.3. So with that in mind, if I have m equals 5, how many total fringes are there going to be underneath the diffraction envelope? So you'll always have this one at the center. So this one right here, I'm drawing now on the diagram. And then you'll have the m equals 1 fringes on either side, and then the m equals 2, and then the m equals 3, 4, 5. So the m equals 1 interference fringes, there are 2 of them on either side of the central max. So if you go out to m equals 5, you'll have 5 fringes on one side, 5 on the other, plus the central max. So 5 plus 5 plus 1 gives you 11. So that's how many fringes will fit underneath the central diffraction maximum if the first diffraction dark fringe is out at 5.3, at m equals 5.3. Does that make sense? Ask questions. It might be easier if you turn on your microphone. Okay, I see your mic isn't working. So did it make sense, or did you ask a question? There are a bunch of things on here. P equals 1 is where the first order diffraction minimum occurs. That's right. P equals 1 is where the first diffraction minimum occurs, where the central maximum ends on one side. That's correct. Yes. Oh, I see. And then I was going back earlier. So to find the maximum m. Okay. So does it all make sense now? I hope. Good. Okay. Any other questions? You're welcome. Okay. Good luck tonight on the quiz, and I'll see you again on Tuesday. Bye-bye.